The last class we were discussing about the taboo search. Now coming back to our genetic algorithm. In this class we are discussing, or we will be discussing, about the advanced operators and some of the advanced techniques in genetic algorithm. And some of these terms are included in the advanced operators or advanced techniques, but we have already seen these techniques like some crossover operators or some mutation operators that we have already seen. But still, we will be looking or going through some of these advanced topics. And these are the contents that we will be discussing about the low-level operators like diploidy, dominance, etc. Then the inversion as well as reordering type of crossovers. Actually, these are the partially matched crossover, order crossover, and the cycle crossover. These are types of crossovers, but these are related to the reordering of the strings, reordering of the chromosomes. That is why they come up in the advanced techniques type. So let's see them one by one. The diploidy as well as dominance. Till now, what we have discussed is about the single strand chromosomes. They are also known as the haploids. If an organism is having only a single strand chromosome, then it is known as a haploid. But when the complex animal life came into existence, this single strand chromosomes were not enough to describe all the properties or all the characteristics of the being, that particular animal or particular living beings. So that is then what happened is because of this chromosome structure has to become very complex in that case. So what happened is that the diploid or double-stranded chromosomes came into existence. As you might be knowing that the human beings as well as the complex living organisms or the complex animal life is relying upon this type of diploid chromosomes. That is, they are having two different strands. Two different strands are coming up or are available in that chromosomes. That is why it is known as the diploid. And obviously, there is chances of triploid and tetraploid as well as higher order ploids, that is multiploids, are also possible. But we are limiting our discussion to diploids only. So that is two-stranded chromosomes. In till now, what we have discussed is only about the single strand, and the chromosome is having only a single string in that case. So in the diploid form, a genotype, you know that the genetic representation of the thing, the genetic representation of the chromosomic representation of the thing, carries one or more pairs of chromosomes, each containing information for the same function. So that is it. Even if in the diploid form there are more than one, that is two chromosomes are present, that is a pair of chromosomes is present, each of these chromosomes will be containing the same information for the same function. And depending on the dominance among these two values for the same function, we will be selecting the function for that particular gene. So let us consider a diploid chromosome structure where different letters represent different alleles, that is different gene function values. That is, in this case, P, Q, R, S, and T are the different allele values. That is, the capital P is there as well as small p is there. Capital Q is there, small q is there. So this each one represent two different characteristics of the same function. That is, an allele. In this case, in this particular gene, if you consider this particular gene, the alleles for that particular gene is either capital Q or small q. That is, either it can take capital Q or it can take the value small q. So in that case, one is dominant over the other in these alleles. Out of these two alleles, one will be dominant over the other. So each locus of the letter represents one allele. That is A. In the previous case, if P and P is considered, here we are both are having the capital P, but small p is also possible there, because all other letters are having a small letter representation. So small letter p is also possible in that case. Then the uppercase and the lowercase letters represented above represent the alternative alleles at that position. That is what I said. That is the capital P and small p is possible in the first gene. The first gene, that is the alleles of that particular gene, is capital P as well as small p. Originally in nature also, the allele may represent different phenotypic properties, like the Q may represent gray-haired gene, and a small q may be representing the black-haired gene. You might have studied in your school days, that is, or in biological classes. That is, out of these two genes, I mean two chromosomes available in human body or human being, each gene represents each specific properties of that particular man. So depending on the gene present or the allele present in that particular gene, the property of or the characteristic of that human being can change. So as an example, in the previous case, this case, if this particular capital Q may be representing, maybe we are not saying that it is representing, but it may be representing the gray-haired property or the gray-haired characteristic, and a small q may be representing the black-haired characteristic. So even though there is a pair of genes exist and describing each function, there should be some aspect to decide which of these two values to choose, because in the case of a human being cannot have both gray-haired as well as black hair at the same time. That is normally not possible. That is commonly not existing. Either a human being is having a gray hair or he will be having black hair. So both these things coming together is not commonly found out phenomena. So the phenotype, that is the physical value for that particular thing, can be either a gray hair or a black hair. So, but in the chromosomic representation or in the genotype type representation, both are existing together. So in that case, the basic approach for eliminating this conflict of redundancy is through a genetic called the dominance. There comes the dominance. The concept of dominance is coming up where there is a conflict in the case of diploidy or diploid type of chromosomes. So at a locus, it has been noted that one allele called the dominant allele will take the precedence over the other alternative allele. So that is, if there are two alleles present in the same position, so considering these two chromosomes, these two pair of chromosomes or pair of these diploid, if we are considering this diploid, this here it is a capital P and here it is a small p. So one of them should be the dominant characteristic. So, or the dominant allele, also known as the dominant allele. So then that particular allele will be considered or will determine the property or the characteristic of the final thing. So that is it. This, but still there is a concept of, or there is a characteristic. That particular characteristic is present in that particular allele. Here it is present. This allele is present in that particular gene, but the dominant one is capital B. So what happens is the capital B comes to here, and out of these two, the capital letters are the dominant one. We assume that the uppercase letters are the dominant ones. So in that case, this capital Q comes in the second place. Then out of these two, say here both are there is small r as well as capital R comes, and here both are capital S. So this also should be capital S, and here both are small t. So that means the small t has to come up here. So out of so decoding this particular diploid chromosome, what we will obtain is capital P, capital Q, capital R, and as well as capital S, and then the last letter will only be the small case. This is because the dominance is for the uppercase characters or uppercase letters. That is our assumption. Then the dominant gene is expressed when the heterozygote, that is a mixed PP, is coming up, then capital P is coming up, or homozygote, capital S, capital S. So then again it is coming up capital S. And the recessive gene is expressed only when the homozygote, small t is coming up. So that is, if a capital letter comes up or a dominant allele comes with a recessive allele, in that case the dominant allele will take over it. Or if both are dominant alleles, obviously that dominant allele will take over the position. And if both the positions are recessive alleles, that is small letters, so small letters in this case, so in that case only the recessive allele will take over. So then the advantages of this one is the diploid chromosomes lend advantages to individuals where the environment may change over a period of time. So that is even when the environment changes, that is the search space. In our case, even if it is the search space changes over a period of time, the small, that is the recessive gene is still present in that particular chromosome. So that will give us a chance of reviving that particular gene or that particular allele for that particular gene in a later period of time. That is the one advantage. And the disadvantages is currently it is harmful. Currently it is harmful means currently these type of representations are not much being used in the case of genetic algorithms, because one is it is very complex, and the other one is this may not be giving you good results, but potentially useful alleles can still be maintained, but in a recessive position. So that is one of the disadvantage. So in a genetic algorithm, the diploidy might be useful in an online application where the system could switch between different states. So that is the condition. If the system, the particular algorithm or the particular code has to switch between two different states or different states, so in that case, the diploidy may be useful. But it is not much employed in the case of our normal problem solving applications. But in the case of online applications or multi-strategy applications, it is being employed. Now coming to the inversion as well as reordering, these operators, most of these operators we have already described, and some of them are not described that much. So the inversion operation condition. So that is the primary objective of the inversion operation is the is a type of mutation itself. That is in order to recode a specific problem. So the inversion operation, 2 points are selected at a random at the length of the chromosome, and then this chromosome is cut at these 2 points, and then it is switched or reversed. Those two, the substring is reversed. So that is the inversion. So like this one, this is a chromosome, and inside this chromosome we are selecting 2 cutting points. This is a cutting point and this one is the cutting point, and whatever is inside this one, so that is this one, this is what is inside this between these 2 cutting points. Then these 2 are reversed using the inversion operator, or inside the inversion operator this is reversed. So 0 1 1 1 becomes 1 1 1 0. So that is it, 1 1 1 0. This becomes 1 1 1 0, and then the rest of the things becomes the same, 1 1 as well as 0. So that is our common inversion operator, or the mutation, inversion mutation operator. That is the same thing, that is inversion happens. But in the case of complex problems, this can be used to retain the original position of the values. Like if these positions are represented with 1 2 3 4, 5, 6, 7, and 8. So these positions are referred with these numbers. So these numbers can be retained in the case of inversion also. That is 1, 2, then 3 comes here. 3 was here. 3, 4, 5, 6, 7, and 8. So that is, if we keep this particular position, so that means we are keeping that particular what you say, that particular scheme means kept or kept in the memory. That is actually what we are doing. So by reordering this particular gene, by ordering, I mean not gene, this particular chromosome in this order, by reordering it in this order, we can recreate this particular gene. So that is, I mean, this particular chromosome. That is the importance of this type of inversion operators or operations. So the features of this inversion as well as crossover are combined together in order to produce alternate or other offsprings, other solutions or other possible solutions. This inversion as well as crossover operators are combined together, and by combining these two, three different crossover methods are generated, and there may be more than 3, but in the textbook these 3 are mentioned. So these 3 are based on the reordering as well as inversion type working, inversion type operator, combining this inversion as well as crossover operators. They are the partially matched crossover and order crossover and cycle crossover. Somebody has already described about the partially matched crossover, and I think I have already taken or discussed about the order crossover, and even if we haven't discussed, I will discuss it today, and then the cycle crossover also. So in the partially matched crossover, what we do is 2 strings are aligned together, and then 2 crossover points are selected. The crossover points are selected randomly, uniformly, and as well as randomly we are selecting the 2 crossover points, and then inside, whatever is coming inside in between these 2 what you say, these 2 crossing points, these crossing points are creating a matching. It creates a matching. So then after this matching is done, then a position wise exchange is done. A position wise exchange within that particular gene, I mean chromosome, is done. So like in this case, 3 and 2 is matched together, 6 and 7 is matched together, 5 and 9 is matched together. So what happens is, in this particular gene, I mean in this particular chromosome, the 9, I mean 3 and 2 are replaced or swapped together. 3 as well as 2 is swapped. 3 and 2 is swapped. Then 6 and 7. 6 and 7 are swapped. Then 5 and 9. 5 and 9 are swapped. In here also, in the parent B also, 2 and 3 are swapped. 2 and 3 are swapped. Then 6 and 7. 6 and 7 are swapped. And 5 and 9. 5 and 9 are swapped. So that is what is the partially matched crossover. So what we obtain in this case is, so as I said, the original one is here. These are the original parents, and 3 and 2 are matched. I mean exchanged. 3 and 2. 3 and 2 are exchanged. So 3 and 2, they are exchanged in the child. And then 7 and 6 are exchanged. 7 and 6 are exchanged. Here 7 is here and 6 is here. They are exchanged here. And then the next one, 5 and 9. 9 is here as well. Sorry, 5 is here and 9 is here in the parent. So that is interchanged. So likewise in the child B also, this is done. So this is the partially matched crossover. So that is each chromosome is having a partial mapping with the other chromosome. So that's it. Then the order crossover. In the case of order crossover, what we do is the order in which the alleles appear or the genes appear is kept the same, but they are rearranged, but the others are rearranged. So in this case, the order crossover applies a sliding motion instead of point by point exchanges. In the partially matched crossover, we were doing the what you say, the point by point exchange was being employed. But here what we does is we applies a sliding motion, fill the left out holes. So let us see how it is being done. Consider two parents A and B. Then in this case also we are considering two crossover points. So this is the crossover point and the first one, this is the second one. So this 5, 6, 7 and 2, 3, 10 are the within this crossover points. So from the first one, what we take is 5, 6 and 7 is in between the crossover points. So in the second chromosome, second chromosome, wherever this 5, 6 and 7 comes, we are deleting the values. We are deleting the values of 5, 6 and 7 from the B, from the second chromosome. So 8, then 7 is here, so 7 is removed and a hole is inserted. Then 1, 2, 3, 10. So 9, 5 is there, 5 is within this one, so that is to be replaced with an H. 4 and 6, so 4 is there and 6 is replaced with an H. So now, once this particular condition is obtained, now what we do is we fill these holes by sliding from the right crossover point, the second crossover point, that is the rightmost crossover point. This is the rightmost crossover point, and this is taken from the previous slide. So 8H, 1, 2, 3, 10, 9H, 4H. So what we do is the second crossover point is this one, and from here onwards the holes are slide towards the right. So here 9 is there, so that 9 is kept there itself. Then 9 is kept there. Then here is a hole. So the next value takes the position of that hole. So 4 is slided towards this edge. So here comes 4. So then again another hole is there. So what we does is we go to the first position. So the first position, it is 8. So the 8 comes in the next position. So here 8 comes. Then the next, it is a hole. So we leave it like itself. Then the 1 is coming up. So that 1 is coming here. Then this is completed. The length of the chromosome is completed. So we move to the front. So the front. So 2, the next is 2. So that comes here. The next 2 comes here. Then 3. 3 is coming here. Then 10. 10 is coming here. So all the holes are here together. All the holes coming up here together. And these holes are filled with the values that is within, that is left out. So 9, 4, 8, 1, 2, 3, 10. Then 5, 6, 7 is left out. So that 5, 6 and 7 is placed inside this thing, inside this one. So that 5, 6, 7 is in the same order as it appears in the first chromosome. So that is 5, 6, 7. So this procedure is repeated for this with this chromosome also. This chromosome also. Currently we done it to this chromosome, and the same procedure is repeated for the first chromosome also. That is, the 2, 3 and 10 are removed from here. So 2, 3 and 10 are removed from here. Then we start with that is here H, H and H. So 1 is coming up. Then the next item is to be, the next gene is to be taken from here. So the 9, 8, 4. Then here it is filled. So we have to move back 5, 6 and 7. Then the remaining values 2, 3 and 10. So that is taken from here. So 2, 3 and 10. So this is how the order crossover is being done. In a sense, in a look, what we feel is that this value is interchanged with these values. That is 2, 3, 10 is interchanged with 5, 6, 7. Okay, that is right. That is being done. Obviously, that is being done. But see, the rest, what happened is the order is the numbers have other changes also. That is 1984. Here it was 1320. So here it is 1984. That is how that the this particular numbers or these particular items are appearing in that particular chromosome. That order is kept constant. So 1984. So one, then these three are how to move to the inside. It has to move to inside. So 984 comes next. Then 567. 567 has to come here. So this is the order crossover. Now the next one is the cycle crossover. So actually cycle crossover performs a recombination under the constraint that each genes come from a parent or the other. So that is, in this case, we are not bothered about the crossover points. Instead, what we do is, we start with selecting one item or the first item from the first chromosome. So that is C and D. We are considering two chromosomes, C and D, two parents, C and D. And the first item is coming from 9. So the first item, we initially we start with an empty string. And what we do is the first item is inserted into that particular string. So the 9 is placed here. So this is placed here. Now, since 9 is here, in the place of D for 9, C is in the place where 9 comes in C. In that place, D comes 1. So 1 has to be taken from the first chromosome itself, because we cannot take 1 from the second crossover, because 1 is in the first position and 1 for the first position is already filled in. So what we do is the 1 is also taken from the first chromosome. So, and it is placed in that position itself. So 9 is coming up, 1 is coming up. Then here 1 and 4. The 4 is to be taken from the first position, I mean first chromosome. So the 4 comes here, 4 has to come here. Then the next 6. 6 is also to be taken from the first chromosome. So 6 is taken from the first chromosome. So now it is again 9. So 9 is again to be taken from the first chromosome. So that is 9. 9 is already placed here. So we can do nothing more. So that means this forms a cycle. 9, then again 1. So that is cyclically repeating. So we cannot do anything further in this one. That creates a cycle. See that one, 9, 1, 4, 6. So this creates a cycle. So what we does in the next step is that the next item is taken from the next, the second chromosome. So 9, then the second item is taken from the second chromosome. These are the parent chromosomes. So the second item is 2. So 2 is taken, 2 is inserted here. So then inside 2, this 8. Now in the C, in the first chromosome, 8 is in that particular position. So 8 is also to be taken from here. So 8 is taken here. So 8 is inserted here. Now if 8 is taken here, 10 is there. So 10 is also to be taken from here. So 10 is taken. So then again it is 3. Then 3 is to be taken here. So 3 comes up. Then in position of 3, it is again 2. So 2 is already we have inserted it. So after this cycle, it is filled. That forms another cycle. Once this 2 is obtained, then that forms another cycle. So the second cycle is over. So after the second cycle, we have filled in almost except 2 characters we have filled in. So now the next character, the next gene is to be filled from the first gene. So that is 9, 2, 3, 1 is present. So the 7. The 7 is to come here. Isn't it? It is to be 7 here. So it is 7. Then it is to be taken from the first one. Then it is 5. Then 5 is to be also to be taken here. So 5 is taken from here. So here there is a small mistake. This is to be 7 and this is to be 5. So that is a typing mistake in the text. So this is how the cycle crossover is being done. So that is the name of this particular crossover or this particular method came up because it forms a number of cycles. And so today we discussed about some of the advanced operators inside the genetic algorithm that is being used inside the genetic algorithm, like diploidy, dominance, and 3 types of crossovers. And that's for today. Any doubts?